Okay, so last section we're going to look at is, again, 8.5, part 4 in your book, 5.6 on the worksheet for tonight, but it's vectors in 3D. So everything that we've done up until now has been on the XY plane, right? We've had the XY axis. So if you can visualize that as being like a box, think of this as like the bottom side of the box, and all of our vectors have been drawn somewhere on the bottom of the box. What we're going to do now is come up off the bottom of it. Okay, that's going to give us 3D, and that gives us the z-axis. In 3D, it can be a little tricky to figure out which axis points in which direction. So the way you can remember, if you're trying to visualize it, is your index finger always points in the direction of the positive x-axis. Your middle finger points in the direction of the positive y-axis. And then your thumb will automatically point in the direction of the z-axis. And you have to use your right hand to do this. Okay. If you use your left hand and you line up the x and the y-axes, what happens is the z-axis goes the wrong way. Okay. So because you use your right hand to figure out the directions, this is called a right-handed coordinate system in 3D. Okay. So any questions on it? Just generally, that's just the directions of the axes. Now, you're not going to be doing sketching. Okay, everything we did two-dimensionally with sketching, you can do in 3D. Like you can take one vector, and you can add another vector on the end of it, and then connect the third side. But it's kind of hard to draw that in 3D. Okay? So most of what we do, it's going to focus on numerical stuff. All right, so what I'll do pretty much for every question is kind of review how you do it in 2D, and then see if you can figure out how to extend it to 3D. So in 2D, we have a distance formula. Now, that formula doesn't particularly connect to a vector. That's just how you find the distance between 2 points. But it's an easy formula to work with. So it's a good kind of warm-up to working in 3D. After this, every formula we do is going to have to do with vectors. All right. So in 2D, they would have to give you 2 coordinates. Each coordinate would have an x and a y value. And if you find the distance between the x's and square it, the distance between the y's and square it, add them up and take the square root, that is called the distance formula. And the distance formula is really just what formula?
Pythagorean theorem.
It's really just the Pythagorean theorem. That's all it is. Yep. So now we're going to extend the distance formula to 3D. Well, in 3D, your 2 points, we're calling them P1 and P2, they have an x value, a y value, and now they have a z value. So when we want to find the distance in 3D, we still have to do what we did before. You have to find the difference between the x's and square it, plus the difference between the y's and square it. And there's going to be one more part to that formula we have to add on to the end. And it's going to follow the pattern that you can see right there. Does anybody have a guess what the last part is that you need to add on to the end to make it 3D? Yeah?
Difference of z's and square root.
The difference between the z's and square root. That's pretty much how every formula we extend to 3D is going to work. If you know the 2D version, you just have to do it like one more time to make it the 3D version. Okay? You gotta add one more part to the formula. Okay, so what this really is the Pythagorean theorem, but it's 3D Pythagorean theorem. Okay. It's 3-dimensional. Let's see if we can find the distance between those 2 points. Okay. Whenever you are using the distance formula, what's the first thing we should usually write down. That's part of the formula.
The square root.
Yeah, put down the square root because everything has to go underneath that. Okay, so we're going to put down square root. And what's going to be the first calculation that I do in the square root?
In parentheses, you do the second x point minus the first x.
All right, so in this case,
4 plus 1 squared.
yep, so it's going to end up being a plus because it's 4 minus negative 1. Okay, so I'll change that to a plus in a minute. Okay. What's going to be the next part of the calculation underneath the root?
Negative 2 minus 3 squared.
So you have negative 2 minus 3 squared, and that would be it if it was 2D. Now the 3D part. What?
It would be 5 minus 2 squared.
5 minus 2 squared. Okay, so we'll simplify all of that. 4 plus 1 squared.
25.
It's going to be 25. What's negative 2 minus 3?
Negative 5.
And when you square that,
25.
25 again. And 5 minus 2?
3.
3. And when you square that?
9.
9. So what is the distance between P1 and P2?
Square root of 59.
Square root of 59. Okay. If they want an exact answer, you need to leave it with the root. If they want a decimal, then you could type it in and round it off. Okay. Any question about finding the distance between 2 points in 3D? There'll be one of those on the list. Okay. Vectors. Okay, so that's a good formula to start with because it kind of shows you the idea of what we're going to do with every formula with vectors. Take the 2D version, add something onto it to make it 3D. Okay. In 2D, we call this unit vector notation. A and B are the components. A was what component before? Okay, so the x-axis component, yep. Or when we draw it in 2D, that's always what direction?
Horizontal.
That's always horizontal. And B is the y-axis, which is always vertical. When you're doing it in 2D, you can say horizontal and vertical because it makes sense in 2D. When we get to 3D, we can't really say horizontal and vertical anymore because 3D, that doesn't make as much sense. So in 3D, how many components do you think we're going to have to the vector? We're going to have 3. We're going to have the x-axis component. Okay. We're going to have the y-axis component. And then we're also going to have the z-axis component. The component itself is a c. That'd be the number that's in front. These are the vectors. Remember, we think of these as like building blocks. Right? We stack i's together. We can stack j's together. And now you can stack k. Well, I was going to ask you the next one. It's k.
Yeah.
And that's the one that is coming three-dimensionally. So i's would stack along the x-axis. J's would stack along the y-axis. And then the z's would be coming at you. Right? That's like the 3D. That's the k component. So that's how you can write a three-dimensional vector in the unit vector notation, or you can also write it with the angle brackets. Angle brackets, A, comma B, comma C. Essentially, every vector we've done up until now, you could think of it as being 3D, where the third part was a 0. Okay? There was no third part. So if the third part is a 0, well, technically that's 2D. Right? But if you memorize all the formulas for 3D, they automatically work for 2D. You just ignore the last part. You don't need it. Okay, so A, B, and C are the components. Not going to say horizontal and vertical, because then what would I say for C? Like horizontal, vertical, and the coming at you component? That doesn't sound right. So x-axis component, y-axis component, and the z-axis component. And if you were going to sketch it, the best way to do it is probably with like software on a computer. So that way when you sketch the vector in 3D, then you can kind of rotate it around and look at it from different angles. Because it's really hard to sketch something 3D on a 2D piece of paper. It only gives you one perspective of the 3D. Okay, that was one of the last things we did the first day we talked about vectors. I told you that this notation doesn't tell you where to put the vector. You can put it anywhere you want. But if you start it at the origin, it has a special name. Does anybody remember what you call it? If your vector starts at the origin.
Is it position vector?
Yeah. It's called a position vector. Okay, so if a vector starts at the origin, that's called a position vector. Oops, not that page. And just as a reminder, in 2D, how you get a position vector, you do that. Kind of like distance formula, but you don't square anything, so it's a little different. And you don't square root. But you do find the difference. Okay, so that would be for 2D. x2 minus x1, comma, y2 minus y1. Okay, so that's review. The order is important. Okay, when you are subtracting, if you do it in the wrong order, you're going to get the opposite of the answer you want. So you have to do terminal minus initial. Okay, and you already have all that in your notes. That's from earlier. Okay, now in 3D, instead of your initial point and your terminal point just having an x and a y, now it has a z. So what do you think the formula to find a position vector in 3D is going to look like?
x2 minus x1, comma, y2 minus y1, comma, z2 minus z1.
Yep. So it's the same as the 2D formula. We're just extending the calculation one more time to include the z's. Yep. So this is finding a position vector in 3D. Okay, so now let's set that up and see if we can find it. So I've got negative 1, 2, 3, and 4, 6, 2. All right. Remember, order is important. What's going to be the first? What's the calculation for the x-axis component?
4 plus 1.
Yep, it's going to be 4 minus negative 1, which will become a plus 1. And the calculation for my y-axis component?
6 minus 2.
6 minus 2. And the calculation for the z component?
2 minus 3.
2 minus 3. All right. So what is that if we do it out?
5, 4, negative 1.
5, 4, negative 1. That's the answer in what the book called the algebraic form of the vector. How about if you were going to write it as a unit vector?
5 by
So you'd stack together 5 of the i's,
4j,
and you'd stack 4 of the j's,
and then -1k.
and then down 1, yeah, negative k. Okay, either notation is correct, and you could see either type on the test. Any question on finding a position vector in 3D? Okay. All right, so the next thing, adding, subtracting, multiplying, scaling, and magnitude. Okay, all those are the 4 formulas we did together in 2D. Okay, so to show you each of those formulas, first we're not doing a visual, so we're not going to connect the vectors, head to tail, which is the end of one to the beginning of the next. We're just going to use a numerical method to add them up. If you want to add vectors together in 2D, you would do x1 plus x2 and y1 plus y2. Well, now in 3D, we have one more step, z1 plus z2. So you can combine the x components, the y components, and then the z components.
Did you put the symbol underneath for plus and minus?
Yeah, so that means plus or minus. Yeah. So if you wanted to subtract them, then you would do, and you were doing v minus w. V would come first, w would come second. x1 minus x2, y1 minus y2, and z1 minus z2. And then when we put a number in front of a vector like 3v, what do we call that number?
Scalar.
That's a scalar. So if we had a scalar product in 2D, remember I said think of it as like a distributive property. You multiply your x component by your scalar, then your y component by the scalar, and to extend it to 3D, what else are we going to have to do?
Multiply
It times the z component.
times the z.
Yep, take the scalar and also distribute it to the z component. Notice when you're scaling, that has nothing to do with 2 vectors. It has to do with a single vector multiplied by a single number. Where up here, it was a vector plus another vector. That was 2 vectors. This is not 2 vectors. It's a number and a vector. Okay. And same with this last formula. That's just a single vector. That's not 2 vectors.
Mr. Hager?
Yeah.
Can you go back up?
So when you add a vector to a vector, what do you get
A vector.
as a result? A vector. How about when you subtract vectors?
A vector.
A vector. When you scale a vector,
You get a vector.
you get another vector. When you scale it, there's 3 things that could happen. What are the 3 things that a scalar can do?
You can get bigger, smaller, or flip.
Yeah, get longer, get shorter, or flip direction. So results, vector, adding, vector subtracting, vector with scaling. What does that mean? Magnitude. When you find magnitude, what is the result?
A number.
It's just a number. Represents how long something is. In 2D, that was your formula to find the magnitude of a vector. What's going to be on the end of it to make it 3D?
Z squared?
Which Z?
Z1.
Which Z?
Z1.
Z1, because we're using V. If you were using W, then this would have been x2, y2, and z2. Right, so to find the magnitude of a vector, take each component of the vector, square them, add them up, and then take the square root. Okay, we're not going to do an example of each one, but I'll go through 2 or 3 of the formulas right there. Right, let's start with adding. Okay, so this is a vector plus a vector. So the answer is going to be
A vector?
a vector. Yep, so we're looking for an I, a J, and a K in the final answer. If you're not sure whether you should use the IJK notation or the other one, use the notation they give you in the problem. Okay. They gave me IJK, so let's stick with that. All right, so if we add those two vectors up, what's going to be the new x-axis component?
5i.
5i. 2i plus 3i. What about the y-axis component?
Negative j.
So it's negative 1 unit on the y-axis, so negative j, and the z-axis component,
3k.
plus 3k. So that's the unit vector notation for adding two three-dimensional vectors. All right. Now we're going to find the magnitude. Okay. Magnitude, kind of like distance formula. First thing you should always put down is what?
Square root.
Always put down your square root. All right, so we got that. What's going to be, there's going to be 3 parts to it. What's the first part?
2 squared.
2 squared, which is 4. Second part?
3 squared, which is 9.
3 squared, which is 9. And the third part?
4.
Negative 2 squared, which is 4.
17.
So that's 4 and 4 gives me 8. And 8 plus 9 gives me how much?
17.
17. So that's the exact distance between, that's the exact length of your vector. Any question how to change that to a decimal? Okay. And last one, part C, is a scalar product. So we're finding 3w. In this case, what does the 3 do to w?
Makes it bigger.
Yep, makes it bigger. How much bigger?
By 3.
3 times as long. Yep. Does it change the direction?
No.
No. If it did change the direction, this number would have to be what?
Negative.
Would have to be a negative. Okay, and it's not. Good. All right. So what is 3w going to be?
9i minus 12j plus 15k.
So triple each component, just like distributive property. 9i minus 12j plus 15k. All right. And what kind of product was that called?
Scalar.
That's a scalar product. What's the other kind of product we learned about?
Dot.
Dot product. Okay, so dot product in 3D works exactly the same as dot product in 2D. You're going to extend the formula just like you would think. So I'm not even going to put the 2D version up because we just did that yesterday. So let's jump right to 3D. All right. What do you think the first step is going to be to find the dot product in 3D between those two vectors? Oh, scroll down? Yeah.
Multiplying them.
Okay, multiply what times what?
x1 and x2.
x1 times x2. Okay.
And then multiply y1 times y2.
Something right before that.
Add them.
Add them. And then multiply y1 times y2.
And then add z1 times z2.
And then add z1 times z2. So this z plus z1 times z2, that's the part we didn't have yesterday. But that's what makes it 3D. Okay. So let's see if we can find the dot product. Sorry, it keeps jumping. See if we can find the dot product between these two vectors. So v is 2i minus 3j plus 6k. And w is 5i plus 3j minus k. All right. if you want, you can get all that ready. All right. First two numbers that I'm going to multiply to get my dot product.
2 and 5.
2 and 5. Okay, Alex, how about my next two?
Shit. 3 and 3. -3.
Can you say it one more time for me?
-3 and 3.
-3 and 3. Yep. So -3 and 3. And shall we the last two?
Positive 6 and -1.
Positive 6, -1. Okay. So Aiden, 2 times 5 is going to give me how much?
Oh, 2 times 5 would be 10.
It's going to give me 10. -3 times 3, that's going to give me -9. And 6 times -1? -6. 10 minus 9 gives me 1. And 1 minus 6?
-5.
-5. All right, that's how you find the dot product in 3D. Any question on how we just did dot product? All right, and the last thing we looked at was an application of the dot product. What did we do with it? Yeah? We used it to find the angle. So angle between two vectors in 3D. What was the formula to find the angle between two vectors in 2D? You need something equals and then something.
Cosine theta equals v times w over the magnitude of v times the magnitude of w.
And what was that numerator again?
Numerator,
Yeah.
vector v times vector w.
How do we say that though? Because there's two ways to multiply with vectors.
Yeah.
Dot product of
V dot W, yeah. So the numerator was V dot W and the denominator was the magnitude of V magnitude W. That part was fine. And that's all equal to cosine. Well, in 3D, that's your formula. How's that different from the 2D?
It's not.
It's not. Okay, the reason it's not different is because each individual part is already different. This is a three-dimensional dot product, which we just did up above. This is a three-dimensional magnitude, which we just did over there, and another three-dimensional magnitude. So the formula itself is the same, but the individual parts to the formula all have that third component in them, like right there. But the formula is the same. And does anybody remember what formula this really comes from?
all the cosines.
It comes from the law of cosines, yep. Where you know all three sides of a triangle. There's your two vectors. You're just making the third side, and then you know side, side, side. And you can find any angle you want. But we're looking for the angle between the two vectors. Just like that, right there. All right, so let's find the angle between U and V. If you notice, these are the same two vectors. Bless you. Those are the same vectors we just did the dot product for. 2, -3, 6. 2, -3, 6. 5, 3, -1. 5, 3, -1. So we already know the dot product. What was the dot product?
-5.
-5. So there's my dot product. We don't know the magnitudes, so we do need to find those. All right. What's going to go underneath the root to find the magnitude of U?
x1. Oh wait. Yeah. x1 squared plus y1 squared plus z1 squared.
Okay, and now if we fill in our numbers, what would that look like?
2 squared
Negative
plus
3 squared.
negative 3 squared, which is
Yep.
9, and then 36.
So 2 squared, 3 squared, 6 squared. The negative isn't important when you square it because it's just going to go away. So I would be careful though, because if you do plug in the negative and you don't do it in the right way on the calculator, it will mess you up. For example, if you do negative 3 squared, what should you get?
9.
You should get 9, but you get negative 9 there.
I
Right?
put it in parentheses.
It's because you didn't put the negative in parentheses. So if you do that as part of a problem, you're going to get the wrong answer. So you're probably better off to just realize the negative is going to cancel, and you don't need it when you are finding magnitude. I'm not saying you never need it, but you don't need it for magnitude. All right, what's 4 plus 9 plus 36?
Square root of 49.
Square root of 49, which is 7. Okay. How about magnitude of v?
25 plus 9.
Plus
So 25, 9, and 1. And magnitude of v is 35. Okay, so we got our magnitudes, got our dot product. When I plug everything into the formula, what's that going to look like to find my angle?
Cosine of theta equals negative 5 divided by 7 times square root of 35.
Yeah. So that's how you want to write it. And we're trying to get theta, not cosine theta. So what are we going to do to get rid of cosine?
Take the inverse cosine.
Yeah, take the inverse cosine. That's going to cancel. And when you type that in, inverse cosine, and be careful when you type it in because the denominator has two things multiplied together. You do want to put that in parentheses. I'll show you what happens if you don't. 7 square root 35. That's how you want to type it in. So the correct answer is 96.93. Here's what happens if you don't put parentheses. Can't even get an answer. That's actually probably the best thing that could happen because you got something that said error. A lot of times when you don't put parentheses, it won't even say error. It'll just give you a different answer. So if you accidentally did that, you'd get lucky that the calculator said it was an error.
Do we have to be in degrees for this?
Whatever mode it says in the problem. So what did I say it was the first time? 96.9.
96.93.
96.93. So again, the correct way to type it in is just like that. Okay. Any questions on that one? Okay. So that pretty much reviews everything from 5.6. Okay, so it's really mostly a review from earlier in the week. Okay. And that finishes up everything that's going to be on the test. So that's the homework. So it's page 363. 15, 17, 29 to 35 odd, 41, 43, and 51. Okay, we got plenty of time, so you might be able to finish that. So please use the time to work on that. And what I'll do is put up a list of all the test topics. I'll put that on the board right now. Okay, also I will be after school today if anybody wants to come for extra help. So this is good.
Usually it ranges in C's every quarter.